Yeah, so this is a quick one on radiation exchange between differential surfaces. So we're dealing with two really small surfaces. Surface 1, in which it's emitting radiation. So we have radiation, this is a hot surface probably, and it's emitting radiation in all sorts of directions. And it's doing it, we'll say it does it diffusely, so it emits radiation in all directions uniformly. So just as much radiation going vertically as is going horizontally. And then we've got surface 2, another really small surface, and this surface is receiving some of the radiation that comes off of surface 1. So if I drew arrows out, it's receiving some of this radiation that's coming off from surface 1. But there's also a lot of radiation from surface 1 that's completely missing surface 2, so it's not being received, of course, radiation in all these directions. Of course, none of the radiation coming in this direction is being received by surface 2. So what we want to figure out is the amount of radiation that is being received by surface 2 that's being emitted from surface 1. And what I've drawn for convenience are the unit normal. So surface 1 is this flat black surface with a unit normal sticking outward, and same thing with surface 2. This is surface 2 with its unit normal sticking out in this direction. I'm going to get rid of them for the time being because there's a couple of things that are worth considering. When we think about, or considering in terms of how much radiation is being received by surface 2, one thing to consider is the angle of surface 2 relative to surface 1. So if I arranged surface 2 like this, you can imagine if that angle is its unit normal, if it points directly at surface 1, or it's completely perpendicular to the radiation impinging on it, it receives a lot more radiation than if it was at an angle like this. So this angle, most of the radiation just goes by it, it's not received. And in this limit, this angle, there is no radiation being received whatsoever. Everything just passes by it, assuming this surface is infinitely thin. So all the radiation just scoots by in both directions, and it's not receiving any radiation in that case. So that's one example, or one thing to consider. Another thing to consider is the location of surface 2 relative to surface 1. So if I put surface 2 down here, it's pretty obvious that it's not receiving any radiation in that case. So if I even drew horizontal arrows, radiation coming from 1, for this, it's below even those arrows. And if I bring it up, the amount of radiation received here, the surface area that surface 2 sees of surface 1 is really small if I position it here. Conversely, if I take this and I put it right over the heart of it, or if I move it up into this field up in here, the surface area that it sees, the projected surface area, is much bigger if it was located up in this region, for example. So in this case, this would be the maximum amount of radiation that surface 2 could feel. It's arranged perpendicularly to the radiation, and it is right in front of surface 1. So it's a couple of things to consider, and we'll talk about those mathematically in a second. So I've gotten rid of all the radiation field, and I'm going to draw one ray coming from surface 1 to surface 2. And we're going to say these are differential elements, so they're really small surface area. And I'll call them dA1 and dA2 to emphasize that this is really only a good approximation if they're both small. We'll get into some more complicated stuff later. So I've drawn a single ray, and I've drawn two angles, theta1, which is the angle from the normal for A1, and theta2, which is corresponding angle from the normal to A2. And let's say we want to figure out the rate at which A2 is intercepting radiation from surface 1. So we want to figure out the rate in total watts that A2 is receiving radiation from A1. So this is the working equation that we can use in this situation. I'll explain what these terms mean. So here we've got Q12 is the rate of irradiation that's intercepted by A2 that was generated by A1. So we want to figure this out. And the units on this, we want to figure them out in watts. So the total wattage of radiation intercepted by A2. This parameter I is called the intensity of radiation that's emitted by surface A1. So it's because it's A1's emitting radiation diffusely, I doesn't depend on the angle. It doesn't depend on this angle theta1. So we could say I coming off in this direction, or this direction, or this direction, this direction, I would be the same in all of these cases. The units of I are in watts per meter squared per steradian. So it means the wattage emitted by surface 1 per square meter of surface 1 per steradian. So SR is an abbreviation for steradian. And I'll talk about it in a second, but really what it means is per unit area of target, almost. So it's effectively how big, a steradian is effectively how big is your target, or how big is the target. In this case, the target is A2. How big does that target look compared to A1? This term, dA1 cosine theta 1, is simply the projected area, the projected surface area emitting radiation. So we talked about at the beginning, if theta 1 was, let's say theta 1 was 90 degrees, and that would mean that this differential area would be lined up like this, and there would be no projected surface area for dA2 to feel. So it would be, effectively it wouldn't be shined on at all, because this surface is infinitely thin if theta 1 was in that direction. But as it is, theta 1 in this case looks like it'll be about, we could estimate theta 1's 60 or 70 degrees, something like that. And if we took A1 and we tilted it 90 degrees to the ray, theta 1 would be equal to 0. We'd have to cosine theta 1 of 0 would equal 1, and the projected surface area would simply be this surface area. And finally, we've got this d omega 21, and it's defined as the solid angle subtended by A2 when viewed by A1. So in essence, this d omega is the size of the target. And if we wrote it out, well, the units on d omega 21 are in steradians. So if we write it out mathematically, d omega 21 is the surface area of the normal projected surface area of A2 divided by r squared. So the r is the distance between the center of dA1 and the center of dA2. And this is the projected surface area of AN of A2. So we just say cosine of theta 2 times the differential area of A2 divided by r squared. So you could look at this a couple of different ways. We could say, if you imagined, if you've ever been target shooting, and you look at a target, if the target was, only 5 feet in front of you, it looks like this huge thing, and there's no way you'd miss it with your rifle or bow and arrow or whatever. But if that target, if you moved it back 100 yards or a couple of hundred yards, r squared starts to get bigger and bigger, and that target starts to look awfully small. And in this case, the target, dA2, starts to appear smaller and smaller when viewed from dA1. On the other hand, we could look at the surface area itself, and this is more intuitive, but you have two targets right next to one another. If r is the same, the larger surface area will appear bigger than the smaller surface area. And one other thing we could adjust would be this angle. So you might look at it this way. If this is you trying to hit a target, here's the target off to the right. If I change the angle of the target, and I made it look more like this, it starts to become a real difficult target to hit. The projected area that you're looking at becomes really, really small. And in the limit, if I said theta is equal to 90 degrees, so if I oriented the target like this, you wouldn't be able to hit it because it's infinitely thin. It's simply a plate. And we could do the same thing with A2. A2 in this case is the target. And if I made theta to 90 degrees, the radiation from A1 wouldn't be able to hit that target whatsoever. So finally, if I put all these together, I come up with an expression for the rate of radiation leaving 1 that's being intercepted by 2, and it's proportional to the intensity of radiation. It's proportional to both the area of surface 1 and the area of surface 2. Make either one of those bigger, and more power would be received by A2. And it's also dependent on the angle, so cosine theta 1, cosine theta 2, like I said before. If either one of these equaled 90 degrees, then there would be no radiative transfer, because they would there would be no radiative transfer because they'd be 90 degrees to, or they would be one surface would essentially be parallel to the radiation. And finally, it's inversely proportional to the square of the radius. So if we made r really large, if we moved dA2 way far away from A1, we put it way out in here, it would receive a lot less radiation from A1 than, say, if we moved it real close. So if I took A2, if we put it up in this region, you can imagine it receives a lot more radiation than if it was moved way back in here. So one last thing to do with the terminology. This rate of radiation, I said, was in watts. And you'll also see irradiation by itself. So instead of saying the rate of irradiation, if the question asks you determine the irradiation of A2, it means determine G, which is Q12, so the total wattage divided by the surface area of area 2. So Q12 divided by A2. So you'd simply divide both sides by dA2 in this case, and we'll come up with this expression, where the irradiation of A2 is proportional to the intensity, proportional to the area of dA1 and relates, again, theta 1 and theta 2, the cosine of these two angles, and is inversely proportional to r squared.